As we know, benzene undergoes typical electrophilic substitution reactions and forms monosubstituted benzene as the product. When this monosubstituted benzene is subjected to further electrophilic substitution, it forms 3 possible disubstituted products in varying amounts. The disubstituted product formed in major amounts depends on the reactivity of the monosubstituted benzene. In turn, the reactivity of the monosubstituted benzene depends on the nature of the group that is present on the ring. A group can be either electron-releasing or electron-withdrawing. The group present on the ring orients the new incoming electrophile to any of the remaining 5 positions. Of these 5 remaining positions, with respect to position 1, position 2 and 6 are equivalent and said to be the ortho positions. Positions 3 and 5 are equivalent and said to be the meta positions, and the position 4 is said to be the para position. The position that the incoming electrophile will occupy depends upon the availability of electron density in the ring, which in turn again depends on the nature of the group G already present in the benzene ring. This is known as the directive influence of a group. This influence could either be ring activating or ring deactivating. Ring activating groups are plus R groups or electron releasing groups which make the electron density relatively rich at ortho and para positions of the ring. Hence, these groups orient the new incoming electrophile to ortho and para positions. Ring deactivating groups are minus R groups or electron withdrawing groups which relatively decrease the electron density at ortho and para positions of the ring. In other words, the electron density is relatively high at meta position. Hence, these groups orient the new incoming electrophile to meta position. For example, the hydroxyl group in phenol, due to the minus inductive effect, withdraws the electron from the ring. Hence, ideally, the electron density at ortho and para positions should relatively decrease. But it is found that the electron density at ortho and para positions is relatively more. This is because of the plus resonance effect, which overweighs the minus inductive effect. Thus, the reactivity is predominantly controlled by the plus resonance effect of hydroxyl group. Due to the plus resonance effect of hydroxyl group, the ring gets activated and the incoming electrophile is directed to the ortho and para positions. The following resonance structures of phenol show that the electron density is much concentrated at ortho and para positions than that at the meta position. Thus, ring activating groups are said to form ortho and para substituted compounds in major amounts. Other ring activating groups include NH2, NHR, NHCOCH3, OCH3. Ortho and para directing groups facilitate electrophilic substitution by increasing electron density on the benzene ring and are called ring activating groups. On the other hand, the nitro group in nitrobenzene, due to the minus resonance effect, withdraws the electrons towards itself. Thus, the electron density in the ring decreases. Due to the minus resonance effect of nitro group, it becomes difficult for the ring to undergo further electrophilic substitution reactions. Therefore, the ring is said to get deactivated. In the presence of the nitro group, the electron density at meta position is comparatively higher than the electron density at other positions, and thus the incoming electrophile is directed to the meta position. The following resonance structures of nitrobenzene shows that the electron density is less concentrated at ortho and para positions than that at the meta position. Thus, the incoming electrophile is directed to the meta position. Thus, ring deactivating groups are said to form meta-substituted compounds. Other ring deactivating groups include CN, CHO, COR, COOH, COOR, and SO3H. Thus, we see that the type of group present on the benzene ring influences further substitution reactions in it.